a series of work we have introduced in previous talks. And we'll talk about how to improve the bounds of these three data structures on processing memory and what kind of optimality we can reach in these kind of questions. So let me give you an overview in the first place. First, we will try to reiterate what Phil and Humble has introduced on our backgrounds of processing memory in a very few minutes. Next, I will describe how to design a semi-balanced tree on processing memory with better bounds. And there are lower bounds we can prove on these trees. In the next section, we'll talk about an application to the KD tree, where we can apply these semi-balanced tree techniques directly to it, with also other further applications on both clustering problems and multi-order trees on processing memory. So just to reiterate and remind you of what we are trying to study with architecture level, we're studying the processing memory with the PIM model, where the entire system is composed of the CPU side with a multi-core processor and the PIM side with PIM modules in total. The communication has to be happening through the network, and all of the execution are executed in BSP rounds. For the matrix, we're studying 3 points. The first part is the CPU work and span, which stands for the computation on the CPU side. The second part is the PIM time, which is the maximum computation on any of the PIM cores in order to achieve load balance in BSP executions. The third part is the communication amount, which is a equivalent version of the communication time if we assure that each of the communication on the PIM modules are load balanced. So the design principles, as we mentioned again and again on the processing memory, is that we need to achieve communication reduction, load balance, and low space overhead simultaneously. And this is often hard to achieve. Existing works, as Humble has introduced to us, is the PIMs and trees, which we found out that the PIM systems are good at accelerating trees of both balanced B trees and imbalanced radix trees. And the search communication, as in these two works, can be reduced to order of log P with the base of B in the chunk when the chunking is updated. And one natural question on these is that what other trees can PIM accelerate, since both balanced trees and imbalanced trees can be accelerated? And to get a step further, can we get better algorithm bounds than this log P structure? And what is the optimal bounds we can have, and what are the lower bounds in these trees on processing memory like? So we'll give an overview on this section. First, we'll introduce 2 techniques of achieving an upper bound of log star P, which is called the log star decomposition, which changes the overall structure of these PIM trees, and also the dual-way caching to enable bidirectional searches along the trees. In the final subsection, we'll introduce how the optimality and the lower bounds are proved. First, we're studying this thing called the semi-balanced tree, which is a normal definition, but maybe not so uniformly defined in textbooks. So I'm just reiterating what we write in our paper. So semi-balanced tree mainly means that for each of the internal node, the subtree sizes of its larger child over the subtree sizes of its smaller child is bounded by a factor of alpha. If this alpha is order of 1, then we call this tree to be alpha balanced. So you can see here with 2 examples. When alpha is equals to strictly order of 1, then we call it this tree is strictly balanced. Otherwise, if it is just a constant factor, then we call it this semi-balanced. So for semi-balanced trees, our PIM tree technique can be adopted. As you can recall that how we divide the PIM tree is based on the height notion. But in semi-balanced tree, we can use the notion of subtree sizes to replace the size of height. For instance, in the left part, as you can see, these trees are balanced for skip list or B trees. So we just directly divide them into group based on heights. But for semi-balanced tree, what we only need to do is find out the internal node size or the subtree size for each internal node. And based on these subtree sizes, we divide them into groups. So if we still keeping this kind of notion and keeping the design of the PIM tree, all of the bounds of the PIM tree still holds for these semi-balanced trees. So the second question we want to address is that what better bounds we can achieve better than these PIM tree. For instance, we can sort out the history of our works. For the PIM skip list, what we did is a 2-layer structure, which can lead to order of log P communication per query. This is the very first work in our group. For our second work, the the PIM tree, we adopted a 3-layer structure. Each of the layers adopted a different replication strategy, but the overall result is that we achieve order of log p communication per query. So as you can see, there's like a very intuitive guessing over the overall result is that can we further extend the design of this replication? And to achieve that, if, for instance, if we apply R+1 layers of structures with R layers of replication, and can this lead to order of log applied by R times P communication recursively? And the answer is yes. And I will show you like how to do this. So the first part is trying to divide these trees into a log star P decomposition. And for each of these components, after the decomposition, we apply a different strategy. Let us recall the previous work on our PIM tree, which we used to reduce communication. Basically, we did this 3-group or 3-layer B tree, where on the first layer, we adopt a fully replication. On the second layer, we adopt a partial replication. And the overall takeaway is that although this tree is like order of n over log p sizes of nodes, we just need to replicate each of the nodes order of log p times. So in such way, in each of the group, the space overhead, the update overhead can be bounded to constant, while all of the searches can be bounded to like a local search through a PIM module in a load balanced fashion. So this is like a 2-way replication. So what we need to do is that we extend this replication directly with similar partial replication strategy. And also, we do need to mention that all of these replications are based on the subtree sizes of this notion. So we can extend this to log star P groups in each of the group except the group 0, where we adopt a fully replicated strategy. In group 1, group 2, group 3, we just replicate the partial descendant subtree onto the same PIM local memory as what shadow subtree does. And in each of the group, for instance, in group I, the subtree sizes, for each of the subtree size that lies in this group is order of log applied by I times P, so that the replication factor is also this number. And the space, as you multiply the number of nodes in this group by the number of replication you need, you can find out that the space in each of the group needs order of n space. So as a result, if we divide this into log star P groups, we can have order of n log star P space to enable all of these like internal searches along the group to be local. The main results after we applying this log star P decomposition is like this. First, the search is PIM balanced due to we still adopted the push-pull search as introduced in previous talks. Next, the communication is reduced to order of log star P query because we only need to cross the borders between the groups. In each of the group, it is local. And it is also work efficient, which means that the total work of the PIM side and the CPU side is order of magnitude the same as the work of shared memory multi-core algorithm of state-of-the-art. The space overhead, although we need to be multiplied by a log star P factor, this is like acceptable in practice because in practice this log star P is also nearly constant. So I will stop here for a while to see if there's any questions. Okay, so we'll continue the talk. The next part of the talk will be the dual-way caching, because as you can see in our previous talk, all of the searches, no matter it is get or predecessor or range queries, are searched from the root to the leaves, which is top and down. But in many of the trees, we need these like bidirectional searches, or even many of the trees are unrooted. So like we need like all these bidirectional searches on each of the edges. So the idea is also to extend the original shadow subtree method, because as you can see, a full replication on the topmost layer is supporting this bidirectional searches inherently. So we just need to modify the part of this partial replication. In prior work, such as PIM tree, we only replicate the subtree on each ancestor to accelerate top-down searches. For instance, each of the internal nodes only caches its local descendant subtree. So what we did is actually we can do like a dual-way caching where not only we replicate the descendant subtree, also we replicate a path from this node to its ancestor in the same group. So in such a way, we can support both top-down searches and bottom-up searches in either starting from any of the internal nodes, whether up or down. And there's like some mathematics in our paper proves that such kind of caching is actually symmetric. It means that the bottom-up caching is taking the same update and space overhead as the top-down caching. So this is only adding a constant factor over all of the cost matrices. For partial, it means that such dual-way caching is only restricted inside each of the levels or each in the same group. It will not cross the groups in order to keep the good bounds in all of our PIM tree stuff. So the main results after adding log star P decomposition and dual-way caching together is that all of these is still kept the same. The only difference is that this search previously is only the top-down searches. Now this search can be between any two arbitrary positions, which means internal nodes inside the tree. And no matter where these two positions are, the paths between them are always crossing log star P groups, which is causing log star P communication. All of these bounds still hold. And in the final subsection, we'll prove that this log star P decomposition is actually optimal, and our upper bound is strictly closing the lower bound in our design. This is the main theorem in our paper of the PIM KD tree, although it's a little bit complicated, so I did some reduction of the original theorem. So basically, if we assume that we fixed the batch sizes. If you're interested in batch sizes, please refer to our original paper. But we just fixed the batch sizes here. Then any PIM-based data structure, which means trees here, that supports order of log applied by G times P, worst case communication per search query, must take space of omega n over G space. So basically, as you can see here, if we choose the G to be log star P minus log star P, the communication and the space overhead is the same as our upper bound design. And as you can see here, how we can achieve this best frontier is that, recall that we did this log star P decomposition, but we can also do a constant factor of G decomposition. So we are keeping only the top G groups or G layers of replication. In such case, this space and communication frontier can be strictly made. This is an optimal trade-off between the space and communication, meaning that if you want to do a search in a load-balanced fashion with low communication, there must be space you need to sacrifice. Due to the time limit, I don't think I have enough time to strictly prove how to do this. Please refer to our paper. The proof outline is to transform this PIM problem to something that seems extremely different, which is a dictionary problem in the cell prob model. This is the existing results from Fox 2023. I guess the author might, I saw him attending the workshop, but he's not here in the audience currently. so the main idea is, as you can see here, there has been a space communication trade-off in both our work and their work in the dictionary in cell prob model. And they're in almost exactly the same format. So what we need to do is to transform these problems together. The key idea is to encoding this PIM KD tree search passes to cell probe words. For instance, if you're going to the left child in a binary semi-balanced tree, then this means that you encode this by a bit 1. Otherwise, you encode this by a bit 0. And if you encode these two together, you can, both of these problems can be easily transferred against each other, so the lower bound still hold. And our upper bound, yes, please.
So in general, lower bounds are hard to prove.
Yes.
So can you just give a sentence or two, what the lower bound in the cell probe model looks like? I mean, is it sort of an adversarial thing? Is it information-based? Or maybe what the cell, and if you just use it as a black box and you don't.
I can explain what kind of this cell probe model is. So basically, is that the first thing is the cell probe model. The cell probe model is that assume that these you have a bunch of data that is resides in cells or cache lines if you use it as systematically. So the cost is that you need to fetch this cell or the cache to the CPU. And as long as something is fetched, the computation takes free. So basically, it's also considering about the space and communication. And for the dictionary problem in cell probe model is that assume you have a dictionary that is storing a bunch of order of log n words. And you have k of such words. So the optimal bits you want to store in this dictionary is something in combination taking C of U over like K bits, something like this. But if you're supporting a dictionary, definitely you cannot just do this compact stuff. So what you need to do is adding some auxiliary structure that is adding additional bits to it. So what this lower bound is trying to prove is that this auxiliary structure must take some kind of like a minimal space in order to achieve this order of G like hops in the cells in order to get what is in the key dictionary. So I guess like we refer to the idea of there is a lower bound, and we know that their upper bound design is expanding the same way as our PIM tree expands. But for the lower bounds, to be honest, it's like a little bit complicated. So I do think it will be helpful if the author is here, but
no, it's fine. It's fine.
Yeah.
Okay.
Yeah, okay. So the basic idea is that these two problems are inherently the same, although they look extremely different. So with the semi-balanced tree, we can have a direct application to the PIM KD tree because in most cases, KD tree are strictly balanced or semi-balanced. So KD tree are textbook space partitioning indexes where it recursively splits a bunch of like area of multi-dimensional nodes into this tree structure. Each internal node stores a splitter. For instance, if we want to split the entire space, we just found the medians and use a splitter over this square. And then like this internal node records the splitter and how you split this node. And you do it recursively. You split these hypercubics into smaller hypercubics recursively, and then recurse towards the leaf nodes where like only one node is stored in each of these leaf nodes. Prior shared memory multi-core bounds of parallel KD trees are the most recent PKD tree where Yang is the author, and also the other authors are also attending this workshop, Ziyang. And so basically, this is like a very complicated bounds of all of the operations they are supporting. But key takeaway in designing their design and our design is that you can see there's a log n or log mn external memory factor inside the multi-core parallel design. And what our PIM tree is trying to reduce this communication factor. One of the challenge we are facing in like implementing these, do you have a question? Oh, okay, sorry. I saw you raise your hand. But in implementing this in practice is that do recall that all of our like PIM semi-balanced tree are based on the notion of subtree sizes. But such information might be hard to be kept in practice. So let me give an example. For instance, if you have some new nodes that is inserted towards the leaf nodes, if you want to keep a counter of subtree sizes in each of the internal nodes, you can see that these countings will soon accumulate to the root nodes. But on the other hand, the whole design principle of our PIM tree is that the more upper part in your tree is, the more times we will replicate it. So this means that actually, because of these two properties, keeping these like counters inside of our direct PIM design is extremely expensive in terms of update cost. And we are trying to avoid that. So the observation here is that these counters are not used to do augmented value on calculation. They are only used to decide which layer of each node lies in. So typically, it doesn't need to be accurate. So our direct design is trying to use a special form of steel counter to keep an approximate value of each of the subtree sizes. And this approximation is accurate enough so that all of the bounds still holds. We use a special form of steel counter where we try to flip a coin when each time a request to increment each of the counter is propagated from the children. And this is a very complicated mathematical formula, which I think due to time limit, I would refer you to our paper to see how this is done. But an example would be that for the lower part of the tree where the subtree sizes are smaller, it will be updated more frequently. But for the upper part, it will be updated less frequently with a probabilistic opportunity to be propagated back to its ancestors. So in such way, like the upper part tree will still be low in update cost because it is like the counters are updated very infrequently. But the tree is still accurate enough to keep semi-balanced properties. And these are the theoretical bounds, where the overall takeaway is that we reduce the communication to log star p, and also translate this to natural language because the mathematics are hard to see on the slides. So basically, all of our algorithms are work efficient in terms of total work. They are PIM offloaded with majority of work going to PIM, and the CPU work is asymptotically lower than the shared memory design. It is highly parallel both in CPU side and PIM side, and the communication is reduced to a log star p factors in comparison with the log n or log m external memory factor. Finally, it is nearly space optimal, where we only have a near linear log star p space overhead, but we proved that this is lies on the optimal trade-off bound, so this cannot be reduced anymore. There's further applications which I think I will go in 2 minutes for each of the page. The first one is that after we develop in these KD trees, we can use them to solve some of the clustering problems. For instance, the very famous 2 clustering problems of density peak and the scan. We can achieve these of the bounds, which also I think it's better to refer to our original paper, where the key techniques is either to directly adopt our design of the KD tree with a small change in one of the augmented value called priority, which is similar as the counter value. The second is DB scan. It doesn't use our tree technique, but many of our, for instance, push-pull search and other PIM techniques can directly be used for efficient grid self-graph construction and also for sorting. The final applications is also on Morton-order trees, which is a work of Guy on LNX 2022, where it is basically a KD tree whose splitting rules uses Morton ordering or Z ordering. As you can see here, Z ordering is trying to to label the space into like sub-hypercubes. This tree is also alpha balanced under 2 assumptions, where it has bounded ratio in the overall sizes, and the distribution has to be bounded expansion constant, which means that the density is continuously changing. It doesn't have like any gaps for sudden changes in the density of these points. And these are very practical data set assumptions in practice. Almost all the multi-dimensional data sets in low dimensions, like almost all of them like follows these properties. And this Morton-order tree is alpha balanced, so we can directly apply our techniques, and all of our previous theoretical guarantees are holding. And also because these Morton-order trees are easier to be implemented on real-world PIMs, we also had some experimental results as we did in the UpMem system, where we have this CPU side and PIM side of 2,048 PIM cores in total. The overall results of these PIM Morton-order trees is still ongoing and under submission. So as you can see here that our yellow bar here, which means our throughput, is better than all of the previous like state-of-the-art shared memory cases on the same machine. And also we reduced these reduce the communication by many factors, because you can see here the memory traffic of bytes per element is in a log scale. So this is like not linear. We're like reducing the memory traffic exponentially. So in the final part, I will go over a simple open problem of like PIM augmented trees. First, currently we only have the technique, as you can see, of these approximate probabilistic counters attached to our PIM tree. So direct accurate counters on PIM is very expensive. As you can see here, we need to propagate all of the P values to the P replications in our design. This is not acceptable in updates. So 2 open questions which are naturally appears is that first, can we design lightweight accurate counters on these PIM structures? And the second, if these counters can be supported, can we even take a step further of supporting PIM-friendly augmented trees? Because like the counter is the simplest version of an augmented tree. If this cannot be solved, augmented trees cannot be solved either. So here are the key takeaways, mainly to reiterate what we have achieved on these PIM semi-balanced trees of all of these good probability results, and they can be applied to a bunch of like space partitional indexes and also the clustering problems. And thank you, that's for all.
Question?
Yep.
It's not my area, but just wondering, in terms of applicability, this is a much more complex data structure than the 2-level or the 3-level before.
Yes.
So in practice, how do they compare? Like, does this one perform a lot better in practice than the other ones? Just,
Well, I think it depends on the architecture heavily. So on the upmap system, because like for smaller data set, there's like no need to keep like these log star p like stuff because the PIM tree will saturate. But for large ones, you can still not like extending them to extremely large ones because, for instance, like keeping force structures might be helpful in practice, as we did in our experiment, but more than like for might not help that much. But from the theoretical perspective, I think closing these bounds to the optimum, like lower bounds, would be interesting, and it tells basically the system researchers that there's nothing more you can do. Like this is the lower bound you can get.
Question? Let's thank the speaker here. Let me just say one thing about lunch logistics. If you're not with another group, you can just go get some takeout, and there's some tables right here on the other side of the wall. So if you want to go, if you're feeling social but you don't have a group, go grab some takeout.